how do we use external memory, both to do the search. We're going to do search using external memory. And then once I've done a search using external memory, and in particular generate some results, how do I actually use those results? You could give a whole tutorial on just this one topic. So what I'm going to do here is I'm going to give 2 specific examples, but I'll give some of the other related work that's gone on here. And the motivation behind this work, which I'm fairly interested in, is that if we look at computers, the processor speeds really haven't scaled for about 10 years, but the parallelization has gone up. And I would guess that everybody here probably has a parallel CPU inside their computer. And what that means is that we really should be looking into parallel algorithms more and more. And of course, Rick, my student, has done very well in the parallel track, and we're waiting to see what the results will be this year of the IPC. I'm particularly interested in how we can not only do sort of large-scale computations, but use the results later. So I'm going to give one example of each of these. So large-scale search is actually been very broadly explored in a number of different domains. Of course, there's people who just do parallel research. They're always sort of asking these questions. In computational algebra, Gene Cooperman has done a lot with the Rubik's Cube and looking at how he was trying to prove the bounds of the maximum number of moves needed to solve different Rubik's Cube examples. And then you see, if we go into the search community, Korf and Rongzhou did a lot up to a number of years ago on doing parallel search. Edelkamp and his co-authors have done a fair amount also recently. And then Reinefeld is actually going to be the invited speaker talking about this topic at SOX. So I'm very excited to see what he has to say. He's been doing work with the 15 or the 25 puzzle, I believe. But let me give a little bit of background here and just talk about what we're doing when we're doing some of this, this search. So I'm going to use an example from Chinese checkers here. At least the numbers are from Chinese checkers. We do a breadth-first search. We're basically trying to generate what are the states at each depth of the search. And we can get statistics back, like what is the width of the state space, which is the level in the breadth-first search that has the maximum number of nodes. We could talk about the diameter, which would be the maximum number of levels that exist. I'm going to talk about undirected graphs here. There is work that looks at directed graphs. They're a little bit more complicated. If we look at this process, what we really want to do is we want to be able to think about it inductively in our heads. In particular, if I've done some number of levels here, and I want to generate the next level, if I tell you the process, given the previous level, how do I get the next level, then you can inductively apply that, recursively apply that over and over and over again, and you'll be able to get the full level. And in order to do this, we can think about sort of 4 classifications of states. We have states that are closed. These are states that I know exactly the depth and the breadth first search, and I'm done with them. I don't really need to look at them again except for duplicate detection, which I'll talk about more in a second. And then I have states that we'll call open. There's really 2 classes of open states. There's open states at the current level. Those are states that I'm expanding right now to generate the next level. And then there's open states which have been generated by the current level and will be in the next level. So I'm sort of always I'm generating these 2 things, and we need them to be distinct, particularly if we're looking at these 2 levels, if I don't want to explicitly store the depth alongside every state. And this is something we don't generally want to do because our searches will be too large. We'll see exactly how we do these in a moment. So we're going to do this process of generating next states, going from the current open to the next level of open. And then we have a whole bunch of states which are totally unknown. They're going to appear at some point in the breadth first search, but I haven't seen that yet. Or I haven't seen these states, but eventually we'll, again, continue this process and generate all of them. OK, so in particular right now, I'm going to talk about doing breadth first searches. And there's a lot of different techniques that have been published using advantage of domain properties. I'm not going to go through every one of these steps. And I'm actually going to focus on using a single machine instead of a distributed machine. And I'm going to focus on using external memory. So external memory is something like disk or a solid state drive. These definitions, the top one and the bottom one should be obvious to most of you. I'm going to make the assumption of ranking or unranking function, also known as a perfect hash, or basically I need to be able to take all the states in the state space and I need to be able to map them, if there's n states, to the numbers 0 to n minus 1. If you don't have that property, you can still do this, but you become less efficient. And so I'm not going to talk about the details of what happens when you're less efficient there. But I'm going to assume I have this perfect mapping called a ranking or unranking. The other thing that's really important to think about here then, once I have this function that can convert essentially from a somewhat, what is the natural representation of a state for generating successors versus what is the natural representation that allows me to compactly store it on disk. Those are almost always completely different. And so an explicit representation so we have two sort of explicit representations. One is sort of the natural one for generating successors, and the other one is this integer representation. But if I'm actually storing those numbers or the bits on the array of whatever I'm using, that's going to be explicit. Those are usually very expensive to store. But when I have this compact mapping that I can do, I can use an implicit representation where the address in memory is actually the identification of the state. Okay? So I don't actually have to store the identity of the state. I just use its address in memory to say, well, this is state 5 million. It's at address 5 million. And then I only need to store 1 bit there, or whatever small information I need to identify that state. So that's a key distinction in the algorithms that I'm going to present here. Now, it ends up that if there were no duplicates at all, doing a breadth-first search is entirely trivial because you just simply go from one level to the next. You could store it all on disk, and you could just stream off one level, you'd generate the next level, and you'd be completely done. So in practice, of course, this isn't the case, and so there's a number of approaches that have been looked at for removing duplicates. And so I'm going to go through a couple of these just to give you guys a sense of what has been done in the past. And these were Rongzhou and Rich Korf did most of this work. And this work, I'm going to assume here, you don't have to do this, but I'm going to assume that each level is written explicitly to disk. And so what I have is I have a file where I've got the previous level. And so the first approach is disk-based sorting. On the left-hand side, I have the file. It's got the previous level. I'm going to generate all the states in the next level. And I'm going to put them on disk here. And we're going to, in this case, Korf used some fancy magic to make sure that actually that we didn't generate states back at the previous level. I'm not going to talk about how he did that. But now I've got the next level here. It's still possible that there's many, many duplicates in the next level because many states could have generated the same successors. And so I can now just do a sorting operation on disk using all the states in the next level. And when I do that sorting operation, all the duplicates will be next to each other, and they can actually just be implicitly removed during the sorting. So generate everything on disk, sort it on disk. There's a little bit faster approach. Sorting generally is an n log n operation, although there are faster sorting mechanisms you can use. The other thing I can do is generate the next level, store it on disk. All the duplicates are here on disk, and then when I'm done with that level, I can put a hash table in memory. And as long as I have a consistent hash function, then all the duplicates will map to the exact same entries. So I read it into memory, the hash table will remove all the duplicates, I write it back out to disk, and then, well, here I'm saying that it's sorted. It might not necessarily be sorted, but all the duplicates will be removed in this process. Another very notable approach is structured duplicate detection. And I'm going to use an example from the sliding tile puzzle, but Rong did this actually in general planning domains. So this is a much more general technique, or it can be applied generally. The idea here is that many state spaces, we can sort of predict where the successors will show up. And so if we look at the sliding tile puzzle here on the left-hand side, on the right-hand side, we have the graph, which is the abstraction of that state space, where we're storing the location of this graph represents the location of the blank. And in the sliding tile puzzle, the blank can only move one space at a time. So if I look at this state up here, B0, if I read from all the states in this B0 state, all the successors will be in B1 and B3. So I could load all the states in the next level in these B1 and B3. And as I generate from B0, I will immediately detect all the duplicates in B1 and B3. And actually then in parallel, if I have memory, or depending on my structure, I could go over here and at the exact same time I could be reading from B5 and I could be writing to B2, B4, and B8. And so what this allows me to do is one in parallel. There's nothing I have to coordinate between different threads here because they're working on entirely disjoint parts of the state space. And then I get this nice division between the labor. And if your abstraction here is not fine-grained enough, that you keep running into collisions here, you can dynamically, he has some papers where he dynamically repartitions the graph to be able to more efficiently do the structured duplicate detection. Of course, down here, now B8, we have to notice that B8, I had like the previous level and the next level. I can read from the previous level of B8 and generate the states in B7, and I actually can do this here because then B5, I'm reading from the previous level of B5, but I'm not writing to the next level. So I actually, at the same time, could do this set of states right here, and I would actually still be able to run in parallel. So this is a nice approach. You need some mechanism to be able to do this structured duplicate detection. So now I want to move to, we're going to use a slightly easier approach for doing duplicate detection in this, what I'm going to describe here. But how do we do breadth-first search larger than memory? And in particular, I'm really interested in storing the results because I'll talk very briefly at the end of how we can use that. And I'm going to talk about two algorithms here. One of them, called 2-bit breadth-first search, it actually minimizes work. The design of this algorithm is designed to minimize the node expansions that I perform. The right minimizing breadth-first search is designed to minimize the writes that I do to disk. So in general, if I have everything fitting in memory, then this actually is a very, let's say I have an implicit representation of my entire state space in memory. Then if I want to do a breadth-first search, I just go through, I find these red states which are at the current depth, I expand them, and I write their successors at wherever depth they happen, or wherever they happen to be in the in-memory array, and I just repeat this. And actually my duplicate detection will immediately occur because I have this entire array sitting here, so I don't, like, the duplicate detection occurs in this array in RAM. So what we're going to do is we're going to move this array from RAM onto disk, and then we're going to see how we can try and do the same process of duplicate detection and generating the next layer if this large implicit array is sitting on disk. So 2-bit breadth-first search is from 2008. We have an entire implicit state space sitting here on disk. I'm drawing this in 2 lines just to say that it's really big, but small boxes here because it's implicit on disk. And what 2-bit breadth-first search does is it divides the state space into buckets that are able to fit into RAM. And so it'll take one bucket, and it'll load that bucket into RAM. And when the state is sitting in RAM, then we see each state is marked as one of 4 possibilities. It's either closed, one of 2 possible open states, or it's a new state or an unseen state. And what we're going to do is we're going to take this bucket in RAM now, and we're going to expand all the states that are in the open list. So the current states are, if I have a successor, then that's marked as new inside the same bucket. I can immediately actually update inside the bucket. And so this is fine. But if I have a successor that is somewhere else on disk, well, I don't know what to do with that state. I have 2 choices. I could throw it away, and then I would have to regenerate it at some later time. Or I can keep a temporary file here where I say, well, here's all the things that I wanted to write to memory, but I couldn't do it right now, or wanted to write to my representation. And if I write to this file sequentially, then I can do that quickly. It's the random access to the file up here that would kill me. So I'm going to have a sequential file where I can write all the states out here. And later on, I'm going to say, oh, later on I want to process this file. And when I do load that bucket in, I'll go through the file of states here. These are stored explicitly, and I'll dump them back out when I have this particular bucket sitting in RAM. Okay? So the idea here is I choose one bucket. I'm going to expand all the states in there. Anything that maps back to the same bucket, I can immediately write to the bucket. Anything that maps somewhere else, I'm going to temporarily store it on disk because I'm trying to minimize the number of node expansions. Later, I'll read that disk and I'll process it and write it back to when I have some other bucket sitting in memory. One of the big complications of this approach is that you will fill up disk. You can fill up disk many, many, many times because the explicit representation, there's duplicates in there. The explicit representation is large. And the other thing is in this approach, it wouldn't be hard to modify it to do otherwise, but in this approach, you're not actually storing it. When you get done, all you know is the diameter and the width of the state space, and that's not too interesting. You can't actually use anything after that. So I was working with a colleague of mine, we published this in 2013, right minimizing breadth first search, and we're going to take the opposite approach. We're going to use sort of the same structure, but we're going to make design decisions designed to minimize the amount of writes to disk, and I'll tell you why that's important in a second. So what I'm going to do is I'm going to use very large buckets, because I'm going to use a slightly different representation, but I'm not actually ever going to load this into memory. What I'm going to do is I'm going to say, look, I'm going to have a bitwise representation of my bucket on disk. And the bits here are just going to be 1 bit per state that says whether or not this bit has been written to for the next iteration. So is this a state that I think will be new in the next level of the open list? So this is representing 1 bucket here. I now read through all of disk, and I expand any state that is open on disk. And any successors that fall into my bucket, I mark in this bit array. And all of their successors that don't fall into there, I throw them away. Too bad. So sad. Now, when I'm done with this, I will write the bit array back to this bucket in memory. And then what I'm going to do is I'm going to move my bucket to be some other portion of the disk, and I repeat the entire process. So I initialize some piece of RAM that represents that bucket. I read entirely through the entire state space. Any states that were marked as open, I expand. So I would have expanded them last time, I re-expand them this time, and then I put them in memory, except this time I'm doing the ones that correspond with a different bucket. Okay. And then, again, I'll write these back to disk here. So the trade-off here is a 2-bit breadth first search is saving all the successors on disk to avoid re-expanding them. The right minimizing breadth first search is computing the successors multiple times to avoid doing a disk I/O. So this is 2 ends of a spectrum and you could actually design an algorithm that's in between. It'd be very interesting to do so. I haven't had time to implement it yet, but if someone wants to do that with me, I'd be happy to. If we look at the numbers here, then the trade-off comes between what is the cost of a node expansion. So in Chinese checkers, node expansions are very expensive. You have to do a recursive search to generate all the node expansions, and you have to be doing duplicate detection in your recursive move generation code. So here what we see is that time is about 10% off here between the 2 approaches, but the right minimizing breadth first search is about the same amount of time as a 2-bit breadth first search. The nodes expanded is using almost twice as many node expansions. But when we look at the disk I/O, it's doing about 20 times less writes and about 8 times less reads. I've seen some experiments that people have been doing. They're doing actually right now. A 250 gigabyte SSD, you can write about 1 petabyte of data before it fails. So SSDs are not designed to do massive writes. So if we look at this, you could do about 10 or 20 2-bit breadth first searches before your disk would die. We can do 20 times as many. So this actually matters if you're going to be using SSDs instead of hard drives, hard disk drives. With a right minimizing breadth first search in Rubik's Cube, it ends up that Rubik's Cube is way faster than for generating states than we are in Chinese checkers. And so we suddenly see here that not only are we 3 times faster, but we get sort of the same gains in writes and reads. Yeah. Dynamic size buckets. So here my buckets are fixed size. You could do this dynamic thing where I was looking at this where you could sort of use virtual memory scheme when in some levels you may not have that many successors and they might actually fit in RAM. And so it's another direction is to sort of like dynamically change your data structures based on how much RAM you're using. And that would allow you in your early iterations and your late iterations to actually be much more efficient. But you spend the vast majority of time, I don't have the numbers here, Actually, I'll show them in a second. You spend the vast majority of time on your really big iterations. And so the savings, if I understand what you're saying, the savings there would not be massive. You might get a 30% savings. But we could talk afterwards. There might be some other things that could be done. So this is just, there's a quick picture here of using external memory. So we could go from there. We could do hybrid algorithms. There's actually some ways we could use structured data more efficiently. I've been working on those, but my implementation needs some improvement. We could do other data. I've been working on generating puzzles for educational purposes. And so if you want to play my puzzle, you can see this here. But you sort of need slightly different types of searches. So this is a little bit interesting to look at this. And in the end, we'd love to have an automatic tuning of state space properties, to decide, well, should I be using the 2-bit or the right minimizing or a hybrid in between? Or what levels should I be doing with the different techniques? There's ways that you could sort of mix all of these together to sort of come up with the absolutely best search at the end. So I have about 5 minutes, but we can run a couple minutes late. Maybe we started a couple minutes late to talk about how I actually use this data. And I'm going to use Rubik's Cube as an example. I assume most people will be familiar with the process of abstraction. So that's the original Rubik's Cube. On the left-hand side is the corner abstraction. On the right-hand side is the edge abstraction. And we use these during search. That is, I come to some state, it's some arbitrary state, and I find out, well, what is the corner abstraction? What is the edge abstraction of these states? I want to look these up in my pattern database to get a heuristic out of them. If we look at the size of a pattern database, what we see is, so 7-edge QBs is about 250 megabytes, so that's pretty small these days, and I get a average heuristic of 8.5 out of that. As I go up to 9 edges, now I've got 19 gigs, so I have a machine with 64 gigabytes of RAM, so I can handle 19 gigs, and I get my heuristic up to almost 10 here on average. As I go to 10, now I'm too big for RAM, but I am able to increase the heuristic value. And actually, we computed what I just described was the 12-edge pattern database is about 450 gigabytes of data. So that's a little bit less than 10 times larger than the RAM I have. And we get a much higher heuristic value here. So the question is, now that we can create these really large heuristics, or I can create this data that's really large, the question is, how should I actually be using this in my search to speed up my search? And so the approach that exists, and actually Rob and Felner, Ariel were both on this paper, is called min compression. And the idea is I'm going to take a segment of entries here, and I'm going to look at these entries, and I say, what is the minimum entry in here? And I'm going to only store the minimum value. So I say 7. Virtually what I've done is I've replaced all of these by a 7. I replace all of these by a 5. I replace all of these by a 4. The actual pattern database that I store is just the 754. So I get, in this case, I'm doing a 5 times compression. If we look at this compression here, and so here I have the 9-edge pattern database to solve some particular problem set. It doesn't really matter. The number of nodes, I look at the number of nodes and amount of time here, about 2 million nodes, 1.5 seconds. So this is using a smaller pattern database. If I use the larger pattern database and compress it by a factor of 25 to be approximately the same amount of memory, I actually get about a factor of 2, a little bit less than a factor of 2 in nodes, and about 1/3 less time. So there's evidence here that I'm much better to use a larger pattern database compressed than a smaller pattern database that just fits in memory. Here, I directly use disk using my SSD. So this is too slow in practice using random access, but it says in theory we could get up to 250,000 nodes here. This took 43 seconds, so it's a complete joke, but it allows us, at least with an SSD now, we can benchmark these algorithms using disk directly, and it doesn't. If we'd used the hard drive directly, it'd use it like 100 times more than this. It's not feasible. So this is actually, the work that I'm going to describe here is something that we have published in SOX this year. It ends up that no one's done an analysis of min compression before, but we were able to do this analysis based on a bunch of assumptions about uniformity of distribution and things like this. And it says actually the expected value of a pattern database, given that I'm compressing it a factor of k, is this subtraction between the probability of a heuristic being greater than I plus 1. If you're interested in the paper, it'll be available soon, but it's actually very, very easy computation here to say what is the loss that I expect to get as I compress a pattern database. And the expected value in the pattern database is actually, Malta's a co-author on this. He did this nice, I had this, and then Malta said, no, you can do this really fancy thing, and you end up with this, which was wonderful, and said this is actually how you can calculate the expected value in the pattern database. So this is there's actually some nice simple formulas for calculating this. And so given this, we can talk about loss of information. How much information do I lose given compression? And so we can see, like, when I actually do compression, so this is just a measure between 0 and 1. What is my loss from compression? My loss is somewhere between like 86 and 90%. The prediction predicts somewhere between, actually I didn't put the IPR here, but the predicted value, we see the predicted value and the actual value. And the model here isn't perfect, but if you actually look at the error in the model, the error is actually about constant. So this is what the Rubik's Cube data looks like if we look at the states here. So we can do them in compression. It's totally general, but we're asking the question, can we do better than that to try and compress things into RAM? And if we look at Rubik's Cube in particular, what you notice is that the first levels, 0 to 9, have about 1% of the states in the state space. And actually, instead of using 6-7 days to generate all of this data, you could generate this in a few hours. And then levels 10, 11, and 12, 10, 11, and 12 have 99% of the data. And so the question is, this is actually called a partial pattern database that was actually published before. Ken Anderson and Rob Holty were working on this. And what the idea here, so we're going to validate this idea on disk that says if I only store levels 0 to 9, which is very little memory, and anything else gets a heuristic value of 10, on this particular data set, I'm going to expand 51 million nodes. If I can store levels 0 to 10, which is 10% of the state space, I'm going to expand 25 million nodes. And 0 to 14, the full data, is 25 million nodes. So actually, the loss I get by throwing away 90% of the data is not very large here. The only problem is, so here I'm using disk directly, so this is just exceedingly slow. But the problem here is, how do I actually throw it away effectively? And if we use a hash table, which is what was described in the original paper, you see here, like, to get up to level 10, I'm actually using 1.6 terabytes. That's more memory than I needed for the compact representation, because you have to explicitly store states here. So we can't really use a hash table directly. There's a lot of stuff. Anyway, come to SOX, and I'll tell you more about these details. But Bloom filters are actually this really cool idea, and I'm going to show how we can use these for pattern databases. So if I want to store a state in a Bloom filter, what a Bloom filter is a membership test. It says, is this state a member of, in this case, a particular level of my pattern database? And so let's say I want to put S1. I say S1 is a member. I use a couple of hash functions, and I look them up into some array, a bit array down here, and I set the bit for every single hash function for S1 to say, yes, it's in, yes, it's in, yes, it's in. I say I have another state S2. I also assign some bits here. Maybe some of these overlap, but I'm going to set all the bits here to be 1 for that S1. And what that means is if I look up S1 or S2 in the Bloom filter, all the bits in the hash functions will be set, and I'll say, yes, S1's in the Bloom filter, S2's in the Bloom filter. If I have S3 now, and I want to look up and say, well, is S3 in the Bloom filter? Now, the correct answer is no. I'm going to look it up, and as long as one of these states is not in the Bloom filter, then I know S3 is not actually there. As long as one of these bits is clear, then I'll be fine. And so S3 will say, no, it's not there. But there's some probability that has to do with p to the k, that has to do with, well, what's the probability that all k bits happen to hit some other state that's already there? And so Bloom filters are something where there's they're lossy. But it ends up that in heuristics, if I'm lossy, that is, I'm going to use a hash table to store the first few levels, and I'm going to use Bloom filters to store the really large levels. if the state is actually at level 9, but somehow I lostily say that it's at 8, I still have an admissible heuristic. So that's the key reason why I can use these Bloom filters. And there's some trade-offs here, like am I going to use more hash functions or less hash functions? Am I use more memory or less memory? So as I use more memory, then the amount of time that's required goes down, the number of nodes that required goes down. If I use the same amount of memory and I reduce the number of hash functions that I use, what you see is that my false positive rate actually goes up, so the number of nodes expansions goes up, but fewer hash functions takes less time, so my time actually still goes down. So what we see here is that if I'm doing min compression, and I won't have time to talk about this, but in the original paper they had, for partial pattern databases, they had proposed something that they called a certain type of compression that ended up working really well. It was actually just an alternate form of min compression. And so you end up with exactly the same performance as min compression here. Our Bloom filters are very effective, although we do sort of get a flat line here. And so there's room for understanding why this line is flat, and can we actually improve performance further here. So I won't talk about the min Bloom filter. And let me just say some next steps. So there's some questions about how we can get better performance by storing parts of even larger levels of using the Bloom filter. We need to apply this to other domains. So lots of questions. What domain does it work? What domain doesn't work? How do you want to combine together hash tables and Bloom filters? And there's lots of other optimizations that could be used to try and get this to work. But at least in Rubik's Cube, we've shown that this is a very effective approach. Takeaways of the whole section on external memory. Lots of interesting questions here, and as our computers, as we have more processors, we are getting more and more RAM, but we even have more disk. If we want to solve larger and larger problems, I think there's a need to study this. There is something here, though. Lots of these research projects, I found, instead of taking sort of 1 year, you do a project and you start a project after ICAPS or AAAI, and you publish it the next ICAPS or AAAI. These projects, because of the optimization and the coding is more complex, it's sort of like a 2-year process instead of a 1-year process, which hurts a little bit. I don't have tenure yet, so next year. But anyway, research in this area I think is really important if we're going to continue to try and scale our performance, because relatively speaking, on a single processor, our portion of the processing power is just going to shrink and shrink and shrink. So I would argue that everybody should be looking at this, or should at least be aware of what's going on here, because it's going to be a more and more important part as Moore's law continues to scale, but we don't get faster processors. When Moore's law stops, then then we'll be in a completely different boat. But anyway, so this has been the first section, really exponential domains here. We have our break right now. We'll come back and we'll talk about polynomial domains and multi-agent pathfinding. And the next 2 sections are going to be are really going to be surveys. So we're going to talk about a lot of different topics, and the goal is going to be, like in polynomial pathfinding or polynomial techniques, we want to give you a real sense of what are the broad approaches that people are using and why are they using these approaches. And then multi-agent pathfinding is this funny domain that sort of sits between polynomial and exponential domains, and Ariel will give you sort of a broad level overview of what is known there and also what is not known.